In this module, we're going to talk about real gases, gases that deviate from ideal behavior, and the van der Waals equation, which is an equation that attempts to describe this deviation. So, first of all, what causes a gas to not act ideal? Remember, an ideal gas is one that obeys the kinetic molecular theory. And basically that means that the volume of the gas particles is negligible compared to the volume of the gas. Now, of course, a real gas, the molecules take up some volume, but when that volume starts becoming a larger fraction of the total volume of the gas, that causes deviation from ideal behavior. Another thing that causes deviation from ideal behavior is when the molecules are moving around in there, doing the things they do, as they come close to each other. Remember, the ideal gas, or the kinetic molecular theory for an ideal gas, says that there's no interaction between the particles, that as they come close to each other, there's no attraction. Well, in a real gas, that attraction, is significant. So the greater that attraction, in reality, the more the deviation from ideal behavior. Now, what conditions cause deviation from ideal behavior? Well, high pressure and low temperature. Why? Well, when you increase the pressure of a gas, basically you're squeezing the particles close to each other. And when you do that, a couple things happen. One, because there's less empty space, the fraction of the volume that's taken up by the particles themselves is actually greater. And that causes deviation from ideal behavior. Also, as you force them close together, they have more of a chance to interact, and their interactions become important. Now, temperature, high temperature. Low temperature. Low temperature means that, remember, the temperature is directly proportional to the average kinetic energy of the particles, which means low temperature means they're moving slower on average. Because they're moving slower, again, as they come close to each other and pass by, there's more time for them to interact with each other. What does that do? Well, the pressure of a gas is caused by all these particles hitting the inside of whatever container it's in. Imagine like a metal cylinder or even a balloon maybe. Now, remember, pressure is force over an area. And these particles are, really light because they're atoms or molecules. So they don't have much force, and the surface area is actually pretty small too. But any individual molecule or atom of gas that hits the inside of a container, its pressure is going to be really small. But the total pressure in there, it's just the sum of all those particles hitting at any given instant. Now, as the particles zoom past each other, if they move slow enough, if the temperature is cold enough and they can interact, what that causes to happen is it causes them to slow down a little bit, and then when they hit the inside of the container, they hit it with less force, and that means less pressure. And so we would expect the pressure of an ideal gas to be greater than the pressure of a real gas. In terms of volume, we would expect the volume of an ideal gas to be less than the volume of a real gas, because in a real gas, the actual particles are taking up space. So let's look at these graphs. For an ideal gas, because PV equals nRT, PV over nRT should equal 1. So this dashed line represents ideal behavior. Now what this is doing is it's looking at several different gases at different, versus pressure. Now, all these lines deviate pretty much from ideal behavior, but notice the deviation gets worse the higher the pressure. So that's high pressure doing this. Down here, less than 1 atmosphere, then you start getting back to ideal behavior. Also, look at the different gases. Now, these all are non-polar molecules: carbon dioxide, hydrogen, methane, and nitrogen. But that means that the only intermolecular forces we're talking about are called van der Waals forces. And so basically what we're seeing here is the heavier molecules are deviating more from ideal behavior than the lighter molecules. The lightest is hydrogen, right? Notice that? And it's the closest to being a straight line and hitting this dashed line. Now let's go over here. When we look at just one gas, nitrogen, and we're looking at different temperatures, notice the higher the temperature, the closer this line gets to being flat and close to the ideal behavior. So now let's look at an equation that lets us attempt to calculate real pressures and volumes, the van der Waals equation. So the ideal gas law is P times V is equal to nRT. I use the subscript ideal here to denote that. This is the van der Waals equation down here in yellow. It says that the pressure plus some factor times the volume minus some factor is equal to nRT. So this pressure here, everything in the square brackets, we want to get to equal the ideal pressure. So the van der Waals, or the real pressure, we have to add something to it, because remember, as these particles are moving past each other, they're slowing down, decreasing the pressure. They don't hit with as much force, so the pressure is less. So we have to add a term to get that up to be equal to the ideal pressure. Now, in a real gas, the volume is going to be bigger than an ideal gas, because we have to include not only the empty space, but the actual volume taken up by the particles themselves. And so we have to subtract something from the real volume, this NB factor. And that should still be equal to nRT once we take those into account. Now, here, N is still moles, V is still volume, and in R and T is temperature in Kelvin. These letters here, A and B, these are called van der Waals coefficients or factors, and they differ by gas. You don't have to memorize any of them, you look them up. This is a little table of some of the van der Waals coefficients. And so if you're doing a van der Waals calculation, you just look up A and B. Notice that this is a cubic equation in terms of N. So I'm not going to ask you to solve a cubic equation in here, which means that basically it's also a cubic in V. So basically it can only ask you for the pressure or the temperature. So let's do a little example. So we're going to calculate the pressure exerted by this many moles of carbon tetrachloride at this temperature in that volume two ways, using the van der Waals equation and the ideal gas law, and compare them. Well, let's do the ideal gas law first. Well, PV equals nRT, so P is equal to nRT over V. And I get like 4.34 atmospheres. And check my calculations. Oops, that's supposed to be a parenthesis there. And I converted my temperature to Kelvin. Now, I'm going to calculate the same thing using the van der Waals equation. Now what this is if you go back and look at the van der Waals equation, I just rearranged it to solve for P. So I divided both sides by V minus NB and then subtracted A times N over V squared. And I get this. So I'm not going to put the units in here because it's just for space. It gets really bulky when I do that. But you should put the units in on your own paper and see how they work out. B and A I looked up for carbon tetrachloride. So there's carbon tetrachloride, there's my A, and there's my B. So when I plug all these guys in, nRT over V minus NB minus A times N over V squared, this thing here ends up being 10.1 liters atmospheres on top and 2.28 liters on the bottom. And this whole thing ends up being 0.667 atmospheres, and I divide, I get this number here, and you do the subtraction, I get 3.78 atmospheres. So, for an ideal gas under those conditions, we have a greater pressure than we calculate for a real gas using the van der Waals equation. And that's what we'd expect, because remember, in that real gas, as the particles go past each other, they're interacting, slowing them down, causing them to hit the inside of the container with a lower pressure.